Now, if you recall with capacitors, we defined our capacitance in a couple of different ways. We said that C was equal to Q divided by V, or Q is equal to CV is when we more commonly wrote it. And then we also described our capacitors, their capacitance based on their geometric proportions. That is, C is equal to epsilon naught A over D. And we're going to do a similar thing with the resistors. And that is that we're going to say R is equal to V over I. Right? And that's sort of akin to this definition, that our resistance is proportional to the voltage and the current that you get from that voltage. Okay, the quotient of those. Now, we can think, now we're also going to describe this in terms of the geometric dimensions of a resistor. And as I said, you'll do this in lab where you measure the resistance of, I think you use a piece of copper wire, and then you can actually calculate the resistance, what the copper wire should be, by measuring its diameter and then measuring its length, and you can calculate it based on something we call the resistivity. So anyway, we can think of electricity like water in pipes, and a large pipe lets a lot of water through, so it has a very small resistance. All right. So a big pipe, if I have a big pipe, it's very large, very easy to push water through this pipe. So it has a very small resistance, so just a little bitty resistance. However, a little pipe, it's a lot more difficult to push water through a little pipe, so it has a very big resistance. If you're given the same amount of energy per unit mass, which is going to be sort of analogous to our voltage. So we can think about this, if our area gets big, if area increases, that means that our resistance decreases. Right? So we can have this proportionality between the resistance and the area, whereas the resistance is inversely proportional to the area. Now similarly, if I have two pipes of the same cross-sectional area, but one is shorter than the other, so one short pipe and one really long pipe, which of those is going to have the larger resistance? Well, the short one will have a small resistance, but the bigger one will have a much larger resistance, because it's a lot harder to push water through a pipe that's really long. And the same is going to be true for electricity. It's going to be a lot harder to push charges through a wire that's very, very long. And so we have this direct proportionality between the resistance and the length. Now, just as we did with capacitance, where we had this this coefficient, this proportionality constant, we're going to have a similar proportionality constant. It's a little bit different in that it's different for every material. But we call this proportionality constant the resistivity rho, and the resistance is directly proportional to rho. So some things have a high resistivity, like wood, for example, has a very high resistivity. And then some things have a very low resistivity, like copper, for example, has a very low resistivity. All right? So with objects with our materials with a high resistivity have a lot of resistance, and materials with a low resistivity don't have much resistance at all. So we can combine all these three relationships, and we get this expression for resistance. R is equal to rho L over A. So we saw here that if L increases, R increases. If A increases, R decreases. And finally, if rho increases, R is going to increase as well. So we have these proportionalities and different effects on the resistance. Let's try this quick test. You can try it on your own. I have two wires that are made of the same metal, so that means that they have a constant resistivity. It's going to be the same. And they have equal length, and so the length is also the same. But the resistance of wire A is 4 times the resistance of wire B. So the resistance of wire A equals 4 times the resistance of wire B. And then I ask, how do their diameters compare? All right, so let's look at this. I'm going to give you a little bit of a hint here, or a little bit of a guidance. R is equal to rho times L over A. Notice that I'm asking for the diameter. And remember that the area is equal to is proportional rather, I'll try this proportionality, it's proportional to the diameter squared. All right, so I'm going to have to account for this when I actually figure out what their diameters are. Now I know that the resistance of wire A is 4 times the resistance of wire B. So, and they also have the same length. So I want to know which one is A and which one is B. So here's my big wire and here's my little wire. Which one of those is A? That is, which one has a resistance of A, which has a big resistance? Well, that's going to be the little wire, right? And the big wire is going to be the wire B. Okay, so that means that diameter of A is small, so I can get rid of all of these. Now, I want to come about with this, this factor of 4 here, remembering that I have a square here, and you can pick from either D or E. It is one of those answers. I'll leave that for you. We'll see that again in the concept test, and we'll see the solution to that as well. It's students often have difficulty with that question. And here's another quick test. This is a common way of determining unknown materials, is you can measure the resistivity given a certain resistance measured through Ohm's law. Remember, V is equal to IR. So you can measure the voltage or the current for a given voltage and find the resistance. And then, if you know the dimensions, you can find rho L over A, and you can solve for rho and then pick from a table of known materials and identify the unknown. Let's stop there.